Hello, welcome to the last lecture on approximation algorithms. Today I will discuss something called polynomial-time approximation schemes. Recall that we have defined the approximation ratio, that is the goodness of approximation, as the ratio of the objective achieved by the optimal. For minimization problems, this is a real number greater than 1, whereas in a maximization problem, this is a real number positive but less than 1. So now I raise the question, how close I can make the approximation ratio to 1. Can I make it arbitrarily close? So it turns out that for certain problems we can achieve such very good approximation ratios. To be more precise, I formally mention what I really understand by this good approximation ratios. Good. So the question is, can we achieve rho equal to 1 plus epsilon or 1 minus epsilon, where epsilon is as small as we like? Is it possible? So this is a very big question. Of course, 1 plus epsilon is for minimization problems, 1 minus epsilon is for maximization problems. So can we make rho arbitrarily close to 1? If so, it is a very, very good approximation algorithm. Okay. Today, or in this lecture, we will see that for some problems, these very good approximation ratios are achievable. But there is a catch here. Such a very good approximation ratio does not come for free. Typically, if we make epsilon small, our running time and other resources increase. Okay. So now, if we want to consider this epsilon into picture, running time becomes a function of n and 1 over epsilon. Okay. If we want to make epsilon small, this parameter increases. Okay, so epsilon does not exactly capture the complexity of the running time, but 1 by epsilon does. Okay. So, if I now look at running times of this form n power 1 by epsilon, this is definitely polynomial in n, but not in 1 over epsilon. However, if I consider epsilon as a constant, this is still n power some constant. If it is something like 1/10, so this is n power 10. But if we take epsilon something like 1 over log n or 1 over n, we want to make it very close to 1, where n is the input size, then this function is n power log n or n power n. So these are not polynomial functions in n. On the contrary, if we consider a running time of this form, we go of n cube over epsilon square, then this is a polynomial in both n and 1 over epsilon, the two important parameters. So, with this requirement in mind, I define two classes of approximation algorithms. So assume that A is an approximation algorithm that can achieve this 1 plus minus epsilon approximation ratio. Okay, plus for minimization, minus for maximization problems. we call this algorithm a polynomial-time approximation scheme, and abbreviate it as PTAS if its running time is polynomial in n. And we are not too much worried about where 1 by epsilon appears. It may appear here, but if it is polynomial in n, then we are happy. So thus these schemes are called polynomial-time approximation schemes. If in addition I demand the running time to be polynomial not only in n but also in 1 over epsilon like this, then this is called a fully polynomial-time approximation scheme or FPTAS. The running time is polynomial in both n and 1 over epsilon. Okay. So in the rest of this talk, I will provide an example of a fully polynomial-time approximation scheme or FPTAS. This will solve the so-called 0-1 knapsack problem. I think you are already exposed to the 0-1 knapsack problem, but let me just recapitulate what it is. It is not the fractional knapsack problem, it is the 0-1 knapsack problem. I quickly describe what the problem is. This will also set up our notations that we will use for the rest of this section. So, there is a collection of n objects, O1, O2 up to On. Each object has a weight, let us call it Wi, and some profit, let us call it Pi, profit or value. Okay, Oi, the ith object has weight Wi and profit Pi. Okay. Moreover, okay, so for today's exposition, we will assume that these are integer values. Of course, for Wi, we do not need to make any such restriction, but for simplicity, let us assume both are positive integers. But in what follows, these should be positive integers. Otherwise, the algorithms that we describe will fail. Okay. Although in general, they may be floating point numbers, real numbers, there is no problem, but we restrict the knapsack problem only to this particular case. Pi are positive integers. And then we have a knapsack of capacity C, which once again may be a positive integer. And this capacity means the maximum amount of weight that the knapsack can carry is C. Okay. Now, we need to pack a sub-collection of these objects, OI1, OI2, OIM, in the knapsack such that the total profit of this, that is Pi1 plus Pi2 plus ... Pim, is as large as possible. Okay. Profit Pi1 plus Pi2 plus Pim is maximized, and the total weight of these packed objects does not exceed the knapsack capacity. It is weight of I1, weight of I2 and so on up to weight of Im must be less than equal to C. So this is now a maximization problem. Okay, and this is the constraint. A couple of remarks follows before I actually proceed with an algorithm for solving this. First of all, we may assume that each weight Wi is less than equal to C, because if some individual object is too heavy for being packed in the knapsack, we can simply discard those objects that do not fit individually in the knapsack from this collection. Okay. So, henceforth we will make an assumption without loss of generality that each of these objects individually fit in the knapsack. And the second comment is there may be many greedy strategies like most profitable first or maximum profit per weight first. This actually can be seen to lead to arbitrarily bad solutions. They lead to solutions which can be made as bad as you want. Okay. This greedy strategy works for the fractional knapsack problem, but not in the 0-1 knapsack problem. Anyway, so with this introduction, I go to a dynamic programming algorithm for solving the knapsack problem. Okay. And then we will convert this dynamic programming problem to an approximation algorithm. This will solve the problem exactly. It will compute the optimal version, but it will take too much time. Why? We will explain. Okay. So let capital P be the sum of all individual profits, P1 plus P2 plus up to Pn. We populate an n by P table, let us call it T. Okay, n is the number of objects, P is the total possible profit, and the I comma Pth entry, where I is the object number and P is a profit value. So I is a number between 1 to n and P is a number between 1 to maximum possible profit P. Of course, you may start from 0, but anyway, 1 is okay. The entry TIP stores the weight of a lightest subcollection of O1 through OI, whose profit is exactly P. Okay. So this is how I formulate this dynamic programming problem. So I will build a two-dimensional table. The ith row will consider objects 1, 2 up to I, the first I objects, and I will consider the weight of the lightest subcollection of this first I objects whose profit is exactly P, not less than equal to or greater than equal to exactly P. Okay. So, how do I initialize this? Okay, so here is another thing. If this profit P is not achievable by any subcollection of this, I just store TIP equal to minus infinity. Okay. Because the minimum of an empty set is taken as plus infinity. Okay, so this is lightest. Okay, then first row is initialized as I want to achieve a profit of P and I am considering only one object O1. So only when P is equal to the profit, exactly equal to the profit of the first object, I can have some TIP value, T1P value, and that is weight of the first object. All other profits are unachievable. So it's infinity with this convention. And then for I equal to 2, 3, 4, 5 up to n, I will keep on populating this table in the row measure fashion as follows. So now consider some I greater than 1. Okay. Then I populate TIP as follows. Okay. First, this profit and the new object OI that I am now considering. I am comparing the profit of the new object OI with this P. If the profit of the ith object is already bigger than this column number P, then definitely I cannot include the object I. Okay, because I want to achieve a profit of exactly P, but this is already a larger profit. So in that case, I have to discard the object OI, and therefore I will just check whether it is achievable from the first I minus 1 object. It's exactly the same profit P. Okay. Otherwise, if Pi is equal to P, I have two choices. I either pick only the ith object, and thereby ensuring the profit of exactly p. So this is this case, but then the weight is wi. Or I can also look at excluding wi, the object I, and look at the lightest subcollection of the first I minus 1 items, achieving exact profit p. And if this is lighter, I will keep this. Otherwise, if this is lighter, I will keep this. And finally, if this profit pi is less than p, there are again two choices. One is, I either include the ith object or I do not include. If I do not include, then this is this, like here or here or here, this is this. But if I do include the ith object, so this increases the weight by wi minus 1, but its profit is pi, so I have to achieve a profit of exactly p minus pi from the first I minus object. The objects considered beforehand. Okay. So this is the basic recursive definition used for filling up this table T. Okay. And then when the entire table, in particular the nth row of the table is filled up, this is the maximum profit. Look at this nth row and find the profit, maximum profit P, such that this weight, this T and P stores a weight, is less than or equal to C. Okay, so this is a nice dynamic programming algorithm that solves the optimization problem of 0-1 knapsack exactly. So far there is no approximation involved in it. Okay. So now let us look at the running time of this algorithm. Okay. To start with, let us suppose that the weights and profits are single precision integers. We will later lift these restrictions. And Pmax is the, I introduce this Pmax, which is the maximum of the profits. Okay, P1, P2 up to Pn. And this capital P is the sum of all these profits, and therefore this is less than or equal to n times Pmax. Now, n can be, I would say, n can be arbitrarily large. So, TIP can be the sum of n weights, and therefore it can be stored using big O of log n bits or words. Okay. And the size of the table is n times p, which, if I use this, is less than or equal to n square Pmax. So all these entries we have to populate, and populating each entry involves playing with weights, which can be as big as big O of log n. Okay. So the running time is big O of n square Pmax log n. Okay. So this looks like a polynomial time algorithm. Okay. As long as n square, n is arbitrarily large, but this is a polynomial in n. Also, this Pmax is if it is a single precision integer, however big it is, it's still something like a constant. Okay. The problem comes when we do not restrict Pmax or the profits to single precision integers. We may assume this Pmax may be arbitrarily large. Okay. So, we now allow the profits to be arbitrarily large. And then let us see, this no longer remains a polynomial expression. Why? So, if Pmax is sandwiched between this 2 power L minus 1 and 2 power L, then it can be represented using L bits. Okay. And now let me still continue to assume that the weights are single precision integers, because this does not surface here. Okay. So then the input size is something proportional to NL. Okay. So this profits can be now stored using L bits. There are n such profits. The input size is NL. And the weights, they have big O of n, so I will neglect that. Okay, since they are single precision integers, big O of NL. And the point is that because of this exponential relationship of Pmax with L, this running time is, although a polynomial in n, it is exponential in L. Okay. So this running time is polynomial in this part, but it is exponential in L. So under this realization or consideration or observation, this which was looking like a polynomial time algorithm is now turned to an exponential time algorithm. So somehow I have to reduce this exponential dependency of this running time. Okay. L. Okay. L is already in good shape, but this exponential dependency of this running time with respect to L must be taken care of. This is where the idea of approximation comes into the scene. Okay. So I am now going to describe a fully polynomial time approximation scheme for the 0-1 knapsack problem. So the basic idea is that the problem was created by this Pmax being too big. Okay. What I will do now, this is the trick, I will take a constant sigma and I will later determine what is the value of this sigma. For the moment, let us take not exactly a constant, but some value sigma. And in order to reduce Pmax, I will simply scale down all the profits from Pi to Pi by sigma. Okay. And since we require this to be integers, I will take the floor. Okay. And I will denote this scaled down profits by this prime, Pi prime. Okay. Then what I will do, I will simply run the dynamic programming algorithm with the original weights, but with this scaled down profits. Okay. So the scaled down profits somehow approximately represent the original profits, but there are some errors. Okay. And I will try to minimize that error by a suitable choice of sigma as much as possible. Okay. So with respect to this scaled down profits, this dynamic programming algorithm will give me an optimal solution. Okay. Let us call this solution. Okay. So this is fine since the weights are not changed. The capacity constraint is satisfied. Okay. This capacity constraint is to do with only the weights, not the profits. Now, this dynamic programming algorithm will return an optimal solution with respect to the scaled down profits. Let us call it scaled OPT prime. Okay. And note that this is optimal with respect to the scaled down item profits P prime I. Now, this SOPT prime referred to a recommendation of which objects you take to achieve this profit. If I take precisely the same objects, but now consider the original profits, not the scaled down ones, this gives me a solution for the original knapsack problem. Okay. And let us say that profit is SOPT without the prime. Okay. So, we pack the same objects that achieves SOPT prime, but now consider the original profit values instead of the scaled down profit values of the items. Then the profit that we achieve is called SOPT. Okay. Also, a thing which we have not computed is that if we consider these original profit values and we consider the optimal solution of the original knapsack problem with respect to the original profit values, let us call this OPT. Okay. This is the optimal total profit with the original non-scaled down profits, PI. Okay. Now once again, this OPT recommends the collection of a set of objects. If I now collect the same set of objects and consider their scaled down profits, I get some optimal, some value. Okay. Let us call this OPT prime. Okay. So, let OPT prime be the scaled down total profit of the objects that achieve OPT. With respect to the original profit, this is OPT. With respect to the scaled down profit, it is OPT prime. Now, in order that this is a good, so this is what I have actually obtained, and this is what, that is the best possible solution with respect to the original profit values. But by working with this scaled down profit values, I have achieved this. So, I want to have an approximation ratio of 1 minus epsilon. So, I should have this approximate solution, SOPT or suboptimal solution, should be greater than or equal to 1 minus epsilon of times this actual optimum OPT. Okay. So, what remains is a sequence of inequalities in order to achieve this thing. Okay. That will also recommend a value of sigma. Okay. So, far I have not talked about how we can take this sigma. We will see. Okay. Okay. So, determination of sigma and also rho. Okay. Now, first of all, Pi prime, scale down profit is nothing but this. Okay. In particular, I can write each Pi prime is greater than or equal to Pi by sigma minus 1. Okay. It is floor. So, actually it is greater than Pi by sigma minus 1, but greater than or equal to will do very good, very well. Okay. Okay. If I can write it this way, sigma Pi prime greater than or equal to Pi minus sigma, or I can rewrite it as Pi minus sigma Pi prime less than or equal to sigma. Okay. So, this is just some algebraic manipulation, nothing in it. Okay. Now, I look at the collection corresponding to OPT. The optimal with respect to the original profits. Now, this will recommend some of these i's. Okay. Let's say there are k such objects. Now, if I add these inequalities up for all these objects, so I1, I2, I3, Ik, and add these things up, this will give me OPT, and this Pi prime will add up to OPT prime minus sigma OPT prime. Okay. And this will be less than or equal to k times sigma if there are k objects in this collection. And definitely I know k is less than or equal to n. So, I have this first inequality, OPT minus sigma OPT prime less than or equal to n sigma. I do not like this k here because k is not known, but n is a known quantity. So OPT minus sigma OPT prime must be less than equal to n sigma. Second inequality is that same thing. I start with this pi prime equal to pi by sigma. But this time I will use this pi by sigma less than equal to. And then if I multiply this by sigma, this gives me sigma pi prime less than equal to pi. Now I consider the objects in SOPT or SOPT prime. Okay. And again add these things up for all these objects. Whatever I1, I2, I3, Ik or IL, whatever. Okay. That will give me sigma SOPT prime less than equal to SOPT. Okay. Now I sum this over all the objects or indices I corresponding to this collection SOPT prime. Finally, I note that this is an optimal solution for the scaled version. And this is another feasible solution obtained in a different way. So, this is better than this. Okay, because this is the exact solution for the scaled down version. So, this gives us the last and final inequality. OPT prime less than equal to SOPT prime, because this is the solution, exact solution of the scaled down version, and this is another solution obtained in a different way. Okay. So now if I plug together all these different inequalities, I see that SOPT this is greater than equal to sigma SOPT prime. By using this is greater than equal to sigma OPT prime. And if I move sigma OPT prime on this side, it will be greater than OPT minus n sigma. Okay. So, I want to make this very small, okay, with respect to OPT. Okay. So, by using this, we have ensured SOPT is greater than equal to OPT minus n sigma. But our desire is we should make SOPT greater than equal to 1 minus epsilon OPT. So, if I take n sigma equal to epsilon OPT, this will give me a value for sigma. Okay. Given epsilon and n, this will give me a value of sigma. But the unfortunate problem is that we do not know OPT. Okay. Therefore, you say that you can simply work out that if I take any sigma which is less than equal to epsilon times OPT by n, then this requirement will be fulfilled. Okay. It's a simple matter of working with these two equations. I want this. So, if I take sigma, scaling factor less than equal to this, then for any sigma less than equal to this will be achieved, our desired goal. But the problem is that OPT is not known a priori. Okay. But one thing is for certain, since we have considered only those objects which individually fit in the knapsack, so this OPT is at least as large as P max. Okay. So the object corresponding to P max can be individually packed in the knapsack. Therefore, OPT is greater than equal to P max, or P max is less than equal to OPT. So, if I, instead of OPT, if I use P max, this still gives me achievement of this desired inequality. Okay. So, since Pmax is less than or equal to OPT, it is legal to take sigma equal to epsilon Pmax by n. So, that is now a complete specification of the scale down factor sigma. Epsilon is whatever you want to achieve here. Pmax is the largest profit, original profit, and n is the number of items in the collection. Okay, so we have achieved a very good approximation ratio, and this can be as close to 1 as we like. Okay, I can take epsilon equal to 1 over 100, 1 over 1 million, whatever. This solution will be very close to OPT. Okay, or even I can take 1 over log n. Okay, so that will also give me a very good approximation ratio. But then, what is the running time? Okay, let us see. We have already deduced that the dynamic programming algorithm takes running time n square Pmax log n, but this time we did not work with Pmax, but we worked with the scale down profits. So this running time is n square Pmax, not Pmax, P prime max, where P prime max is nothing but Pmax over sigma, okay, which is less than or equal to Pmax by sigma. And if you look at this, Pmax by sigma is n over epsilon. Pmax over sigma is n over epsilon. Okay, so this is n over epsilon. So if I substitute this here, I get n cube log n 1 over epsilon. So this expression is polynomial in n and also in 1 over epsilon. So this is a fully polynomial time approximation scheme for solving the 0-1 knapsack problem. So this is an FP task for the knapsack problem, 0-1 knapsack. Good. So with respect to approximation algorithms, we have seen quite a few interesting algorithms and use of linear programming techniques for achieving or designing approximation algorithms. Also, we have seen in this lecture an approximation algorithm where the approximation ratio can be made as close as possible, as close as we desire to 1. So I hope this gives you a brief and comprehensive idea how approximation algorithms work. So with this exposure, I believe it is good enough for me to stop. So, bye. So, this is perhaps going to be my last lecture. So, bye. I hope you enjoyed this course, all the parts, and I will look forward to having more interactions with you. Definitely we will do during these doubt clearance and tutorial sessions. But this is the end of my lecture part. Okay, take care.